but to come to the UK. So the Royal Society has these exchange schemes which can fund UK researchers to come to India or vice versa, or both. And there's these Newton International Fellowships that fund non-UK researchers to work in the UK. In addition, there's also the British Council, which funds fellowships that fund non-UK. Sorry, I'm getting some echo, I think, from someone, but yeah, there's these as well, which fund postgrads and PhDs. Unfortunately, the UK government has cut a lot of international collaboration funding, but there has been stuff there in the past as well from these sources, and hopefully it will come back soon. So yeah, if you're interested in any of this, then I'm happy to talk about it, even if you're not interested in coming to work with me or Queen Mary. So yeah, in this talk, actually a lot of it is just going to be quite about the general idea, so not necessarily about my work. And then we're going to sort of look at some of the outstanding problems to do with the idea generally, and how we might be able to solve them. So things to do with can we have, if you make planets very, very early, can the star formation environment still affect the planet formation process and things like that? So about half of the talk is just going to be a very general introduction to the idea here. And so that is going to start off with exoplanets. So in the last decade or so, we've detected many, many exoplanets. There's now more than 4,000 confirmed, and they're very diverse in their properties. So some of that diversity is shown here, where we have planet mass and planet orbital period. And so this line here, beneath that, we just can't really detect planets very well, either because our telescopes are not sensitive enough or because we've not been observing for long enough. But above this line, we see pretty much everything. There's a very large spread in the planet properties. We observe these hot Jupiters that are massive planets on close-in orbits. There are rocky planets that are sufficiently close in that they become molten, so lava worlds. There are rocky planets like the Earth or super Earths. There are also, there we go, the ocean worlds and ice giants, and cold Jupiters too, just much like Jupiter of our own solar system. So we really want to understand why there are so many different types of planets in the universe. You also see things like different numbers of planets per star, different planets depending on whether or not the star is a binary, different planets depending on the star's metallicity. So why is this, and how can we understand it? Well, to do that, you have to understand both, number one, how the planets form, and number two, how they then evolve. And it's the how they form that I'm interested in mostly at the minute. And so planets are known to form from flattened disks of material around young stars. So if you go to look at a young star forming region, you'll see something like this. So there's a star in the middle here with a disk around it. This is a face-on disk, and then this is an edge-on one. So it's turned, so you can no longer see the star. And we've been able to observe these with Hubble since the mid-90s. So we've known about these planet-forming disks for a long time. But in recent years, our view has dramatically improved. So ALMA allows us to look deep within these disks, and they no longer look like smooth structures anymore. They have various rings within them. So there was HL Tau back in 2015 was the first disk with these concentric rings observed, and TW Hydra. And then recently there was this D-Sharp survey, which found all sorts of structures like spirals as well as rings. And so these may be linked to the planet formation process. And so these have had a lot of attention on them. So if you want to understand how a planet is made, most people are currently thinking about how the planet formation process links to these structures. But there's a bit of a caveat here, which I'm going to mention a bit more later. These disks are all quite close by to the sun, and that's because it's easier to resolve the structures. Okay, if they're far away, then you can't see this gap as easily. And that introduces a bias in terms of the kind of environment that you find these disks. So the question is, can you go from something like these D-Sharp disks to exoplanet populations? And because of this bias, I'm worried that you can't. These are useful laboratories for understanding how disks can work, but they can't tell you how you can get all these different types of planets, perhaps. So let's think about where these disks are actually going to be found. I said they're around young stars. Young stars normally form in large clustered groups. So this is the Eagle Nebula. You have here a bunch of young stars, and then around them is the interstellar medium has this great big bubble, and there are also these pillars. Something clearly has happened here, okay, that sculpted this bubble and this pillar. So what is that? And well, we're going to look at a video of that in a second. Of how a region like this forms and evolves. But first of all, let's link this with the disks and look at how long the disks survive for. Okay, so if you were to look at lots of different clusters like the Eagle Nebula, so lots of different clusters in the sky at different ages, and count the number of stars that have a disk, you would get a plot like this. So this is how each of these colors, these blobs, is a different star cluster, and they all have different ages. And then this is the fraction of the stars that have planet-forming disks. So early on, a region, most of the stars would have a disk, and then by maybe a few million years, more than half of them are gone. Okay, and there's essentially none left by 10 million years. So the planet formation process has to happen generally in a few million years or less, given that we think that most stars have planets. So let's now go back to the star. We're jumping around a bit here, but let's go back to the star forming region, like the Eagle Nebula. How did that form? So here I have a simulation from James Dale of a turbulent cloud that is going to collapse under gravity. And it produces these filaments. And at the junctions of these filaments, that's where the stars form. And those stars are emitting ionizing radiation here that heats the surroundings up to about 10,000 Kelvin. Conversely, the gas out here is more like 10 Kelvin. So you have a very hot, high pressure bubble that is driving into the surroundings and blowing away the gas. Now, let's watch it again because it's nice. And the pillar that ends up forming down here is actually this accretion. This is a filament that is channeling material down to the cluster. And because it's quite dense, it just gets left behind for longer. Okay, so all these little white dots here are representing the stars. And then this is the gas getting dispersed. So now let's link these different ingredients that we have together. Well, first of all, this is just a summary of how the Eagle Nebula relates to that picture. So you can visualize what would have happened here. There would have been a cloud that collapsed. These were probably filaments. Then you made your stars. And then this is the very hot bubble. And then the surroundings are cold. So now we'll link the ingredients together. If you were to observe this simulation at 1 million years, this is where you would lie on that plot showing how many stars have a planet-forming disk. It's denoted by this red line. So if I were to observe this simulation, I'd say something like 60 to 80% of the stars should have a disk. And then as we advance through the simulation to 1.5 million years, to 2 million years, we're now in a situation where maybe half the disks are gone. And then by the simulation end time, which I think is that point, more than half of the disks have disappeared. I see there's a question.
Yeah, sorry, I wasn't sure whether to interrupt you or not. So
okay.
The question is, what type of masses or spectral types are you talking about here?
For the massive stars or for the ones with the disks?
No, the plot you've shown here, and you're just tracing the kind of evolution of the disk, right? The disruption of the disk. So, yeah, so what kind of a mass is shown or spectral type is shown here?
Yeah, so I can't know. I can't remember the exact spectral type range covered, but this is going to be something like solar mass downwards, or 1.5 solar masses down to M dwarfs.
Okay, okay.
It's low mass
stars. Okay, okay. All right. Okay. Yeah. Thank you.
So yeah. So the point of this little cartoon here really is just to show you that this is not really a very long period of evolution for stars or for stellar clusters. but that is, in that context, you have the story of planet formation for most stars. Okay, this is quick, but most of the disks are gone in that time. So the point I want to make is that when we're looking at these ALMA images of D-sharp disks, they look very isolated systems, but actually most stars are going to be in this kind of context. And so how can the cluster environment affect the disks? Well, there are many different ways. One is through tidal encounters, gravitational encounters. So that is where one star flies past another star with a disk and perturbs it. So RW Auriga is a good example of this. Here is a simulation of what we think has happened. So there is a star flying past this disk, and it actually shrinks the disk and gives you this big tidal tail. And then here are ALMA observations of that system. So we have the two disks and the tail. And RW Auriga is also launching a very strong jet, and that is probably in part because the disk has been truncated and it's accreting a lot of material. So the disk ends up smaller, and it's putting a lot more material onto the star. So perhaps this could affect maybe not just the disk evolution, but also the planets you might get. RW Auriga is a very extreme gravitational encounter. The star gets very close. But people like Giovanni Rizzotti have looked at, you can hopefully see a movie here, larger simulations of lots of stars in a cluster and looking at the effect of the more distant gravitational interactions on the disks. And broadly, it doesn't seem to do that much. And I'll return to this slightly later. Okay, so if you're not having very strong gravitational encounters, then the effect on the disk is actually quite small. So that's one way that disks could be affected by their environment, is through gravitational interaction. The other way, or one of the other ways, which is the one that I focus mostly upon, is external photoevaporation. So we just saw that movie where the cloud collapses and makes the massive stars, and then the ionizing radiation is blowing hot bubbles. Well, UV radiation in that star forming region is also going to be shining on the disks. So this is just an artist's impression. You have a big star over here shining on this disk and driving material away from it. And so this again could affect the disk. I'll show you some evidence in a second, but it reduces the disk's mass, it reduces the disk's size, and it also reduces the disk's lifetime. So again, this could potentially have some impact upon planet formation. So we directly observe disks that are being photo-evaporated by the radiation of their environment. So the unit of UV field is G0, and essentially for reference, 1 G0 is the local value to the solar neighborhood. Okay, so this is 10 times stronger than the UV in the solar neighborhood, 100, 1,000, 10,000, 100,000. And so in these very strong UV environments, we have been able to directly see evaporating disks since the mid-90s with Hubble, and we call these proplids. And it's very clear that something is happening to them because they don't really look like a disk anymore. They've got these cometary shapes. And then until only 5 years now? Yeah, 5 years ago, we didn't really have any evidence for disks evaporating in weaker UV environments. But Serena Kim recently found proplids in a UV environment that's a couple of orders of magnitude weaker. And back in 2017, I found evidence for a disk evaporating in a really weak environment. But this is a very exceptional case because the disk is so big that you warm it up just a tiny bit in the outer disk and it becomes gravitationally unbound. So this won't be a common thing here. But one of the problems that I'm going to discuss a bit later is that we don't really know how to find direct observational evidence of evaporating disks when the UV field gets weak, because it doesn't really look like a proplid anymore. But we do also have indirect evidence for how the disks are being affected by their environment. So this is some nice work from Megan Ansdell, looking at Sigma Orionis. So there's the star Sigma Ori here. It's an 08 star, I believe. And on the right here, what she is showing is as you get further away from Sigma Ori in projected separation, that the masses of the disks is going up. And so this is quite often interpreted as evidence for the disks that are close to the O star being depleted of mass more quickly than the ones that are further out. So this is evidence maybe that the disk masses are affected by the UV radiation that they're exposed to. Another statistical sort of indirect way of probing the effect of evaporation is from this kind of plot. So here, Guarcello et al. In 2016 are looking at the Cygnus OB2 association, so it's one region, and they've broken that region down into different UV field strengths. And where the UV field is very strong, they don't find many disks, and where the UV field is a bit weaker, they find comparatively more. So again, maybe the UV field here is reducing the disk's lifetime. And the final plot that I want to show, giving statistical evidence for disks being affected by their environment, is not a very nice plot. I have trouble interpreting this. A lot of people do. So what we have here is lots of different star-forming regions. You can think of these as probability distributions. So this is disk size on the x-axis. And then this is the probability that you find a disk of that size or bigger. So essentially where this is steepest, that's your most common disk size. So if you compare Lupus, Taurus, and the ONC, which all have similar ages, ONC here is the Orion Nebula cluster, you can see that the ONC has much smaller disks than these other regions. And the difference is that Lupus and Taurus are low mass star forming regions. They don't have any O stars, whereas the ONC has O stars, has a very strong radiation environment. So not only is the mass and maybe the lifetime of the disks being affected, but also perhaps the size of the disks too. So here's a cartoon just summarizing that. We've gone through quite a lot of plots that are, some of them quite complicated. So the cartoon is that if you take a disk and shine UV light upon it, you can reduce the disk's mass, you can make it smaller, and you can make it live for less time. And maybe that has some impact on the planets you get. But as I will discuss in a moment, that's yet to be seen, yet to be confirmed. So this is another fairly complicated plot. We have talked about the disks being affected by gravitational encounters and by radiation. So which one's more important? Well, Andrew Winter did some really nice work in 2018, comparing the two mechanisms in different types of environment. So here, these plots are the same. On the y-axis, it's the UV field strength. And on the x-axis, it's the stellar number density. So this is a very dense stellar cluster. This one's very sparse. And overlaid here is the range of conditions that we expect for a bunch of different star forming regions. And what Andrew did was study what destroys disks most quickly in different parts of this plot. And this is the result he got. So if you lie to the right of this line in this region here, then gravitational encounters will destroy the disk in less than 3 million years. Whereas if you lie above this line, then radiation will destroy the disk in less than 3 million years. And here they both work together equally effectively. They could both do it. So you can see that for most star forming regions, actually it's the radiation that we care about more than the tidal encounters, at least according to this work. Now, I'm not going to be talking loads about my own stuff, so I'll just mention here that to figure out how the external photoevaporation was affecting the disk, Andrew in this work was using models from myself, which tell you if you shine light on a disk, how much mass it loses per year. It tells you the mass loss rate. Yeah, the final thing which I wanted to mention very briefly, I'm not going into any real detail about this, that can affect a disk is supernovae. So we saw a simulation earlier of a cloud collapsing to make a star cluster, and there was a bubble was blown by the radiation. And then at the end of that, you have a supernova go off. So if you watch this panel down here carefully, and I play the movie, you'll see a supernova going off in this region. And so that injects a lot of energy and momentum into the surroundings. I could give a whole other talk on why this video is interesting, because the effect of the feedback before the supernova really strongly affects what the supernova does to the surroundings. You'll see here that the supernova energy very efficiently just escapes out of the region because there's these holes already there for it to do so. Whereas if you make a supernova go off in a dense cloud, it's a much more destructive explosion. But anyway, that's not today's talk, that's a different talk. And so that supernova shock can affect disks. And so Close and Pittard did some nice work taking disks at different orientations relative to a shock coming in from the left here. And so if the disk is face onto the shock, then it will get very easily destroyed. Whereas if it's edge on, then it can be a bit more resilient to the impact of the supernova. I would just say that, of course, supernovae are not, because most disks only live for a few million years, supernovae aren't expected to affect most disks because the supernova will be going off after about 5 million years typically. The other way that supernovae can affect disks and planet formation is through chemical enrichment. So a supernova will enrich the surrounding interstellar medium with things like short-lived radionuclides like aluminium-26. And some work has shown that the amount of aluminium-26 you have in a planet can affect the fate of the water on the planet. So can affect whether or not you have surface water or water that's embedded within the planet itself, for example. And I don't know very much about this, and I always get asked about it, but based on the sort of amount of aluminium-26 in our own solar system, there has been speculation that the solar system formed in a supernova environment to be enriched by this. But here is some nice work from Mark Krumholtz. This is now a slice of galaxy, so the scales here are kiloparsecs, showing that you don't necessarily need to put a disk right next to a supernova to enrich it with this aluminium-26. And if you're looking at an entire galaxy, you can actually sort of maintain a high amount of aluminium-26 just in the interstellar medium through lots of supernovae going off. So this is another topic that's interesting, but again, how the stellar clusters can affect the disks and maybe the planets. So I started off the science here showing you these disks, which are fantastic laboratories for learning about how disks work, how planets affect disks and how planet formation may happen. But because they're being considered in isolation usually, I think they can only tell us so much. Okay, we have to think about what happens to most stars, which are not in such low radiation environments as these disks are. These are all quite close to the sun, and we don't really have massive stars there. I'm nearly done with the sort of background. So this is another plot from Andrew Winter, and it's got the same axes again. So this is how strong the radiation is. And then this is how many stars there are in a cubic parsec. And so it's the same plot we had before, where we were comparing what's important, the radiation or the gravitational encounters. And what we have here now is not any particular, well, there are some regions drawn on, but this gray scale tells you the probability that this is a theoretical model, that a star will be in any kind of environment. So we know how stellar clusters scale in size and sort of complexity. So you can put that into a model, and we find that most stars are going to be in this sort of intermediate UV environment at this sort of density. The proplyds in Orion are quite rare. We're not saying all disks should be like that, but most disks are going to be sitting in this kind of environment. And then this down here is where we've been focusing our attention with ALMA usually. So this is just to highlight that this is where we need to be looking to understand maybe what happens to most disks. Okay, so
that
now,
would mean that you, sorry.
Yep,
so that would mean that you will be looking away from the clusters, or are you looking at isolated stars?
So I think we need to try and target clusters. So I mean, a good place to start is Orion, for example. So Sigma Ori, Lambda Ori, or you could go somewhere with a strong radiation field like the ONC, but look a little bit further away from the core of it and see what's happening to the disks. A good counter to what I'm saying here is that this is thinking about planet formation locally to the sun, or within the Milky Way, Whereas most, if we want to understand the exoplanet populations that we're seeing, most stars formed back at a redshift of about 2. And there, the metallicity was lower, the star-forming environments might have been more extreme. So actually, perhaps most stars did form in these more extreme environments, if you go back and consider the galaxy evolution. So yeah, there's lots to do in terms of thinking about different environments, but I think no matter what happens, looking down here, these are quite unusual, I think is probably fairly fair. So the question is, what happens if you move up here in one way or another? So yeah, now I'm going to be jumping around even more. This talk does cover quite a few different topics. So what I'm not going to do is spend a lot of time talking about the modeling that I do, but I did just want to mention that is sort of my main contribution to this problem. I have a code, computer code that can model. If you take a disk and shine UV light upon it, it works out the chemistry of the gas. And that's sort of the novel thing. You have to do chemistry to get the temperature right. And then you can solve hydrodynamics to work out the flow structure. So here is a 2D model of a disk that's been shone upon. And we've worked out the flow structure, and it's been projected into 3D to make it look nice. But these are very computationally expensive, which is why they've only been 2D so far. And it's because of that chemistry that you have to solve. And then the other thing I wanted to mention is this one. I have one of my goals has been to try and make research into this more accessible to the rest of the community. Not everybody has a code that can do this, to study how disks are evaporated. So in 2018, I should make the reference clearer, but I published a paper on this thing called the fried grid. And so what that does is, if you have a star with a disk of a certain size, and that disk has a certain mass, and you are shining a certain amount of UV light on it, fried will tell you the mass loss rate from the disk. So that means if you've got a disk evolution code that works out how the disk viscously evolves, you can couple that with fried to work out how it's getting evaporated too. So this is one of the things that I've done that's been used most, I'd say, from my numerical modeling research in this. But yeah, really what I wanted to do was talk about some outstanding problems. What don't we really know yet in this topic, and what might we be able to do to address those problems? So I've got 3 that I'm going to focus on. There are many more. So I'll just mention them briefly, but we're going to go through them all in detail. So one is understanding the true distribution of environments that disks are exposed to. I showed you this plot from Andrew Winter of stellar cluster density and UV field strength. Instead, we're looking at what I think are rare disks, mostly. We have to go and look up here, which is the most common environment. But that was a theoretical model. So how can we actually go about measuring the conditions that most disks see and experience? How can we figure that out observationally? So that's one problem. The second one I've already mentioned, which is we see proplyds when the radiation is really strong. But theoretically, we expect that the disks still lose a lot of mass, even when the UV field is sort of medium strength, or even maybe sometimes weak. So how can we find that and prove it without just using the sort of statistical arguments that I mentioned earlier? And then finally, does planet formation actually care? I think there's fairly strong evidence now that disks are affected by their environment, but does the planet formation process actually notice the environment too? So those are 3 big problems that I want to just go through briefly. So the first one, understanding this distribution of environments. So actually, I'm going to say very little about this one. I'm just going to conceptually introduce it because I don't necessarily have a solution really for this yet. So as I said, the question is, maybe I'll just jump back to show you the plot. It's this plot. This is a model. This tells us where we think most stars should lie in terms of their environment, but how can we check this is right? So one thing you could conceivably do is, if you have an OB star in a cluster and you can spectrally classify it and know how much UV radiation it is emitting, you could then look at where the disks are on the sky relative to that star and just use some sort Of course, it's very rough because it's a projected separation. It's a 2D separation on the sky. And you could just assume that maybe that this radiation gets geometrically diluted. So it just gets weaker as 1 over distance squared. But of course, that's really simple in lots of ways. There's the uncertainty about the true 3D distances. And the other thing is there's probably extinction happening. So these star forming regions are messy clouds with lots of structures in the way that could be obscuring what actually reaches this disk. And similarly, you could have some disks that are embedded. So that's probably too simple an approach. And as I said, I don't really have a solution to this yet, but I wanted to mention this space telescope mission design that I'm involved in called Hyperion. So this is going to be, hopefully, if it gets accepted, a UV space telescope. It's being led by Erica Hamden in the University of Arizona. And its main focus actually is star formation and understanding the evolution of star forming clouds. But one of the things it's going to be able to do as well is actually directly measure the amount of UV radiation that is hitting these disks. So that would potentially allow us to solve this problem. But the issue here is that this is a mission design at the minute. So it may not even get accepted. And then even if it did, it wouldn't be launching until 2028. So there's, I think this is not a problem that we will solve very quickly, unfortunately. So the second problem, how can we observe external photoevaporation in weak and intermediate UV environments? So I've already shown you this plot today. So again, just to remind you, this is how strong the UV radiation is. We use this unit of G0. So where 1 G0 is the solar neighborhood value. This is very strong. This is quite rare. This is very weak. This is quite rare. So based on the previous plots from Andrew Winter, what we're interested in is this middle regime here. So how can we go about observing disks that are evaporating here? And a big part of the problem is that we just don't know what to look for. It doesn't morphologically look that different from a disk. It doesn't look cometary. So how can we identify a wind? So to explain this, I just need to show you what sort of some typical observations of disks might look like. This actually here is a model. But this is a real, what we would call position velocity diagram. Okay, so this disk is spinning around. So maybe this side of the disk is spinning towards us as the observer, and this side is spinning away from us. And the rotation speed is just given by Kepler's law to first order. And so if you were to draw what we call a position velocity diagram, you would see something like this. So this is going from left to right across this image, and showing how fast the material is moving as you do that. Okay, so it's essentially you're just tracing Kepler's law here. This bound here, this line, or this dotted line here, is Kepler's law that says the velocity you'd have as a function of distance. So for a normal disk that's just rotating around, this is what you'd expect to see. All of the emission just contained within contours set by this. So here, G is the gravitational constant. This is just the star's mass, and R is how far away you are from the star. So that's what we normally would expect to see in a molecule like CO, carbon monoxide. And so what I did was take models that I had run of evaporating disks and ask, well, what other traces might allow us to distinguish an evaporating disk from that normal position velocity diagram. So here we have two panels. One is the density field, so log density. And then these are just velocity vectors showing the wind coming away from the disk. And then on the right, we have the temperature, the color. And then these contours are showing where you have different chemical transitions or where certain things dominate in abundance over one another. So the star would be here. This white dotted line is where you'd have a carbon monoxide disk. And then once you go outside of that, then the carbon monoxide gets broken up by the UV radiation. It gets dissociated, and you end up with atomic carbon. And so, and eventually you also get ionized carbon. So looking at these, ionized carbon you can't really observe with any instruments at the minute, local to us. So there's only really Sophia, and that's not sensitive enough to see disks. So atomic carbon seemed like the good thing to look at. So I'm just going to jump back a slide. This is what you'd see in a position velocity diagram for CO. What would you see with atomic carbon, which probes a bit further out in the wind from the disk? Well, you get something very different. So here again is where Kepler's law would tell you the emission should be confined. So you'd only expect emission in here and in here. Whereas if you have a wind, you get material that is moving faster than it should be under Kepler's law. And you also get emission from material in these quadrants here where you don't normally see it. So I'm going to flick back just to show you, if you draw a line down there and a line down there, you don't normally really get emission in these regions, and you don't get emission faster than this dotted line. But you do if there's a wind in atomic carbon. And if you were to observe this same disk in CO, you do indeed find that all the emission is stuck in here and in here. So that's something which is promising. We expect that we can resolve this issue by looking at position velocity diagrams in atomic carbon with ALMA, and that should allow us to fill in this gap.
Excuse me. So are you suggesting that the winds are the evaporated material?
Yes. So I'm sorry, I've not really explained that. So yeah, we would say there's a disk and a wind. So everything outside of sort of this little dense bit here, I'm referring to as a wind.
Okay.
Apologies if that wasn't very clear.
Okay.
You can also get internal winds driven from the disk by the host star, but here I'm mainly just focusing on the environment heating up the outer disk and stripping material from there. Okay, and so yes, ALMA hopefully can detect this, and it's just a matter of time now and applying and keeping my fingers crossed. So the final problem that I'm going to mention today is, does planet formation actually notice the environment? Is it just the disk that gets affected, or could it maybe affect the planets too? And here I've essentially just got a question mark because I don't really know. I don't think anyone really knows just yet. But what I'm going to do is address, or at least compare some evidence against one of the ideas that is normally used to say that planet formation won't care about the environment. So there's growing evidence now that the planets form really, really early. So within 1 million years even. And this is some really nice data from Segura Cox from last year and others. And this is only a 500,000-year-old disk, which is really, really young for a disk. And already they're seeing evidence for maybe these concentric ring features. So maybe there's planets there already. So it'd be a very good argument to say, well, in 500,000 years, you already make your planets, or get most of the way there. The disk is probably still really embedded on this timescale in the star forming material. And then you remove that envelope and just destroy the disk with the radiation, and the planets don't notice the environment. And that is a possibility, definitely. But it still makes me wonder, how early on can the environment affect disks? So what I wanted to do was look for evaporating disks in very young regions. So I'm just going to zoom in on part of Orion here. So here's the Orion constellation. We're zooming in here towards what's called the Flame Nebula. So here the Horsehead, Sigma Orionis. This is the Orion Nebula cluster. And then this thing here, which looks a bit pixelated now, unfortunately, is the Flame Nebula, NGC 2024. And this is the youngest star forming region in the Orion constellation. And to cut to the chase, we looked here in archival data and found 8 proplyds in the region, so 8 evaporating disks. What we have in the middle here is a map of the region with 3 massive stars. So this is a B star, this is an O8 star, I think it's this one, and I think this is another B star. And to the right-hand side of this dashed line, the region is about 1 million years old. And to the left-hand side, it's only 0.2 to 0.5 million years old. So it's very interesting that in this really young region, we're finding evaporating disks on this kind of timescale that would be competing even with really early planet formation. And so what these contours show is Herschel data. And so what we think is happening here is that there's these stars which have just switched on their feedback are dispersing the gas here. They're sequentially sort of unveiling young stars and their disks and evaporating them quickly. And the disk fraction in this region is really low. So you recall that plot showing the number of disks over time. At least with ALMA, the fraction of disks detected was pretty low. So yeah, just as a final point, yes, planets could form really early, and that could shield the planet formation process from a lot of feedback effects. But at least for some disks, that's not going to save you, just because even for really young disks, they're clearly being evaporated, and we have direct evidence for that. And then the last thing on the same point is what my PhD student is working on at the minute. So she has star forming simulations like the one I showed you from Jim Dale, you know, the orange cloud collapsing to make stars with the radiation feedback. And what she's got here is actually, well, so you see the cloud, this is the column density. And then the different points are groups of stars in this cluster. And what she has is the UV history of all of these stars. So by that, I mean the amount of radiation that each point here is exposed to over time. So these stars move around in the cluster. Maybe they start off embedded in a cloud and they have a low UV environment, and then that envelope gets destroyed, and then they get shone upon by strong radiation. So Lynn has the UV history of every star in this cluster, which means we can understand the effect of when they formed and where they formed and things like that. And this is very, very preliminary work at the minute, but she can get plots like this. So this is how much mass a disk loses over time. Ignore these sort of neater looking lines. So what we have here is actually exactly the same star in the model, but this blue line here is accounting for the fact that that star is embedded in gas for some time. And this line here is ignoring the star forming material. Okay, so just to go back, if you had, let's say it was this point here, as that moves around in the cluster, we're tracking the UV field it's exposed to. That gives you the blue line. And then if you remove all the gas and do the same thing, that gives you this red line. So at least for this one star, by being embedded just for a short period of time, you can retain a lot of material for maybe this critical time of 0.5 to 1 million years. So this is definitely very early work. This student only started in January. But with these kind of calculations, we can get a good theoretical idea of the role that star-forming gas has in shielding planet formation from these harsh environments. So does planet formation notice the environment? I think the answer is maybe. Certainly not all the time, I think, because otherwise the imprint upon planets would be quite large. But I think this is yet to be seen. Okay, so I'm done now. So just to summarize, the main point, if a lot of this talk has confused you or something, the main takeaway message is that these planets are formed from disks around young stars, and these young stars form in these clusters. So they're not isolated systems on their own in space. They're being shone upon. They might be being gravitationally perturbed. They're not there on their own. The disks are definitely affected by the radiation and by gravitational encounters. We have really good evidence for this, and it can happen early on. But what we don't have so much is the direct evidence in these sort of weak intermediate environments that we think are common. So we're not able to look at a disk and say that one is evaporating. So that hopefully will be resolved with these atomic carbon observations. And yes, are the planet populations affected too? That's the really big question. And the answer is we don't know yet, but hopefully that'll be coming in the next few years. So that's everything. Thank you very much.
Let's thank Thomas for giving such a nice talk about planet formation. So we now have time for question and answer, and please raise your hand. I see a couple of those. already, and or post your question in the chat box. So you can unmute yourself and ask questions. So first we'll start with Annapurni. So please go ahead with the question.
Hi, Thomas. It was a very nice talk. A lot of questions as such. But let me ask you one thing, that the simulations you had on that your PhD student is doing. So you basically put the stars on orbit and then let everything move and then calculate the changing UV radiation on the disks. Is that what you do?
Yeah, so it's actually, so I should have put in a reference. These are simulations from Ahmad Ali, who he's been doing work on star cluster formation and evolution and feedback. So these calculations are already existing. All we have done is taken the results, and so he actually does it with Monte Carlo radiative transfer. So each source in here, each star sends packets of photons through the grid to work out how ionized it is and how hot it is. But at the same time, because they do that over all wavelengths, you can say, well, if the photon falls into the ultraviolet range, keep track of how much radiation there is in each cell. So this is a grid-based calculation. There are cells here, and you can track how much UV radiation goes through those cells. Okay, and so what we've done here is
on the cells. Okay.
Yeah. And so then after this, so we're not doing everything exactly at the same time. At the end of the calculation here, we have how strong the UV field is over time for each star, and then we can put that into a disk evolution code to see how the disk would evolve as it's exposed to that radiation.
Okay. Do you put in any velocity dispersion for the stars within a population, within the group?
Yeah. So these are just sync particles formed from the collapsing gas cloud. So they end up with whatever velocity dispersion they get from the gas. I'm not actually super familiar with the prescription actually for how so the sync particles aren't artificial. Well, by definition, a sync particle is artificial, but they're formed in a sort of consistent way, so where they inherit the momentum of the gas that they're formed from to some extent. So they move in all sorts of directions.
Yeah, thank you. Just one more question. The one more question is, is there any impact of binaries in disk evaporation in clusters?
Yeah, that's a really, really good question, and not one that I have thought about much, because there's enough sort of problems with isolated systems. So yeah, really good question. So for any given binary, often the neighboring star doesn't have a dramatic impact on the disk through the radiation, just because often the stellar mass is so low that the UV radiation isn't very strong. But binarity, of course, can affect the disk tidally. So you can truncate the disk. That's normally the dominant effect in binaries, but certainly people are starting to think about evaporation externally in binaries, but it's not something I've done much with yet.
Okay, yeah. Thanks so much.
Good question, yeah.
Indranil, you can go ahead and ask the question.
Good talk. I have two questions. First question is that it appears that you have taken a Keplerian disk, right? And while your the radiations due to this star planet system, it is deviating from that line that you say that it is Keplerian, right? You had that hyperbolic, some sort of an hyperbola, right?
Yes. Yeah. So if it's just a Keplerian disk, you'd expect all the emission to be confined between this dotted line and this dotted line and this dotted line. So in here and in here.
Lot of radiation in between. So that means most of the matter is not Keplerian, right?
Yeah, these are hard to interpret. It can also be sort of line of sight effects. So so you would get, I'm just trying to think, because well, you are right in the sense that you get a range of what do I want to say here?
Your simulation, you see that in the inner part of the what you call disk is also very thick. The moment they are getting thick, they should deviate from the Keplerian distribution.
Yeah, you are right. I'm just trying to think what a pure Keplerian disk would actually look like, because this is a real observation. So if it was a pure Keplerian, so I think the answer is that actually it's never in reality a truly Keplerian disk. I think if you have a model where it is purely Keplerian, you do very closely follow these lines, and you don't get so much emission in the interior here. And I'm sure I've got a model somewhere which looks like this. But it's much harder to get something that is super Keplerian. Now, this is faster than you'd expect to have from a Keplerian rotation alone. So this is fairly unambiguous as a signature of an external wind. But yeah, I've not got a very satisfactory answer for why you've got all this filled in stuff here off the top of my head. But yeah, if you do have a model which is a pure rotation, so if I was to make a PV diagram from this, it would just follow this line. Something slows stuff down inside. I'm not sure what it is that's doing that.
The second question is that you are studying these winds from these kind of disks, right? Mm-hmm. But young stars are also known to give very strong jets. So when do you find these winds to dominate, and when would you expect the jets to dominate? Yes,
that's a really good question as well. So I think a lot of attention has been paid to different feedback, the impacts of different mechanisms on disks separately, and now it is time to start thinking about how we link them together. They're probably actually quite linked, external photoevaporation and winds. So what's the best way to frame this? The external photoevaporation is very powerful early on if the disk is large. So what it will do is take a large disk and rapidly truncate it. And by maybe 1 million years, actually the external photoevaporation doesn't do very much anymore. Okay, because if the disk is small enough, it's sufficiently gravitationally bound that the external irradiation just doesn't strip more material. But that act of truncating the disk can help drive a jet. So there is a sort of feedback process there in a sense. But the impact of the jet upon the thermal structure of the disk and things like mass loss and wind driving and how that interplays with external photoevaporation hasn't been directly studied yet. So there's that indirect link, but direct modeling has not been done.
Okay, I see another hand from Yogesh Joshi. Could you please unmute yourself and ask?
Yeah. Hi. So when we see the disk fraction star, there is a function of age. So at a certain age, we see all this profile. So, but for a certain age, we have different kind of clusters having different morphological structures, mass, and even within these clusters, you have different masses of the star. Okay. Yeah. So this disk fraction, can range in this, small window and wide range.
Yes, yeah, that's so. Serena Kim in Arizona is revisiting this kind of plot. So it's this kind of plot you're talking about.
Yeah, exactly.
Yeah. So this is with Iraq. So actually, this disk fraction as well also looks quite different depending on what instrument you use to observe it with. So because it traces different types of dust grains. It's a very naive picture I've painted here, just because I wanted to give the simple idea. So the ALMA disk fractions might look very different, and you could also break. So this is what Serena Kim is doing now, is breaking this kind of curve down into distributions for low UV environments and distributions for higher UV environments, and you get different curves on this plot. So you're right. It would vary as a function of stellar mass and as a function of all sorts of other things, but these prior observations are just bundling everything in together.
Because here we have, a small number of cluster sample. So if we increase the sample, so we may get a better distribution, and we can see the real picture of this.
Yeah, so yeah, I know people are trying to do this, and it's a great thing to do. The better statistics we have on the disk fraction, whatever that means, so with certain instruments, as a function of time, yeah, the more we have, the better. And then once we have enough to get not just good statistics on the distribution with everything thrown in together, we can start to break it down by different parameters, like the mass of the star forming region and things like that. Yeah, and that'll be really useful to do.
Okay.
Saurabh, you can ask the question now. Saurabh, please unmute yourself and ask the question.
Sorry, Thomas. Yeah, thanks for this very nice talk. So similar to Yogesh question, so these clusters, they have plenty of like stars of different mass, and they also have range in their age. And sometimes also the massive star, they trigger star formation. So if you see the, like, I've one of your plot where there is a massive star and then there is a dispersion with the distance. So can it be due to the like sequence in the age also, or and how do you differentiate like the intrinsic effects on the disk? Like there are some massive stars and there are low mass stars, so this will be fraction will be different in this. So you have to like correct for those effects also.
Yes, so another good point. So interrupt me if I'm not answering correctly. So I think there are a few different questions there. So I think one of them was about the differentiating how disk around stars of different masses are affected.
Yeah.
So theoretically, we can do that. So you can, with Fried, for example, that grid of mass loss rates, one of the parameters varied there is the stellar mass. And as you'd maybe expect, if you have a low mass star, and then for a given disk property, so mass and radius, if the star mass is lower, it's easier to lose material because that disk is less gravitationally bound. So you get less external photoevaporation as a function of stellar mass. But there's question marks about what the disk properties are of different types of star as well. So I do maybe low mass stars start with more compact disks than big stars. All of those factors will come into it. So that's I guess that hopefully answers a little bit about how things vary with stellar mass. It's only really theoretical at the minute.
Yeah.
But was there another part to the question I might have missed as well?
Yeah, so like if there is a distribution when you see like effect of like UV radiation on the disk. So there is one plot where there is a massive star and then there is a dispersion ratio, and it increases with when we go away from the massive star. So can it be due to like sequence in the age of those stars? Maybe massive star.
Are you talking about Megan Ansdell's thing, for example, here?
Yeah,
So could this be age related?
Yeah.
That's another really good question. And yes, to some extent so this is something I'm also hoping that Lynn will be able to look at with her simulations too. See, I can't remember what Megan Ansdell did in her discussion on this. She's very good. I expect she probably would have looked at ages, but no, it's a good question. So I think for this particular region, it's actually very devoid of gas now. There isn't much material left in Sigma Ori. It's a great big vacant bubble, and it's quite old. Yeah. So maybe in this region that's less likely, but when you're trying to interpret any given region, it's very complicated and very messy. Yes, because you could have what looks like a very massive disk at large radii, but actually it just formed recently. So yeah, it's a good point.
Also one more last question. Is there any direct measurement of this mass, like apart from these ALMA data, like normal SPSR and ARIES? How do you calculate this mass?
Yeah, it's a good question as well. So, and actually one which is probably another talk again. So there's a lot of problems with measuring disk masses. If you measure it with dust or with carbon monoxide, you get very different answers. So the disk mass measurements are currently very uncertain. I think is probably all I can really say.
Okay,
ALMA's good because it's optically, you can see pretty much all the emission. It's optically thin often, unless you're looking in CO. But yeah, I think the only thing I can say there is masses are very uncertain in disks.
We are going out of time, but we can take another question. Neelam has raised her hand. Could you unmute yourself and ask the question?
Yeah, thanks, Thomas. In your disk fraction slide, there are two symbols. What are those? I mean, one is square and one is circle.
Good question. I'm not actually sure. I assume so they're the same region. It'll be, yeah, so it's the same region. It'll either be a different measurement or a different wavelength, perhaps. So I need to just, I can't recall off the top of my head what these different boxes are, but it'll be either a different wavelength, which would illustrate the point I was saying earlier about how disk fraction, it depends on what you're really looking at, because sometimes there'll be small dust grains left when you haven't got any big ones, or vice versa. So it's either that or it's well, I think that's probably what it is, but sorry again, it's not a better answer there. I can't remember what those different boxes are.
Yeah, and my other question is that how do you differentiate whether this is due to the external radiation field, or this is, I mean, this photo evaporation, or this is due to the source itself, central source itself? Yeah,
that's something which is of ongoing discussion. So internal photoevaporation and external photoevaporation are well characterized separately. And then there's also MHD winds as well, which could be doing something important. And I think the importance of the external photoevaporation, it dominates early on. So if you're within the first million years, then I think external photoevaporation should be more important if the UV field is strong enough and dramatically affects the outer disk. Whereas the internal photoevaporation, the mass loss rates are less usually, but for a longer period of time. So they're probably both important, but in different ways, I think that's what I'd say at the minute anyway. That answer may change.
Thank you.
So thanks, Thomas, for such a wonderful talk again. And we hope to have you here at ARIES sometime in future, and then you can visit us, and we can have more discussion. So with this, we'll close for today, and we'll meet next week for another presentation. So take care, and we'll close it here.
Thanks very much.
Thank you.